All right, we have been talking about limits for just a little bit now and sort of informally taking some limits. It's time, though, to look at the actual definition of what a limit is and sort of formalize what we've been discussing on an informal basis. All right, so for as far as the definition is concerned, first of all, to show it to you in the book, definition of limit is here. It says, let f be a function defined on some open interval that contains a number a, except possibly at a itself. Then we say the limit of f of x as x approaches a is L, and we write it as you see there in the notation. If for every number epsilon greater than 0, there is a number delta greater than 0, such that if 0 is less than the absolute value of x minus a, which is less than delta, then the absolute value of f of x minus L is less than epsilon. Okay, there's your formal definition. Let me write this definition down and talk about what it means as we go. Then I'm going to draw a picture and try and graphically give a better explanation as to what it means. All right, so again, what the book has told us is that the limit of f of x as x approaches a is equal to L if for every number epsilon greater than 0, so the first thing we should gather from this is that epsilon is strictly a positive value. Epsilon can't be 0, epsilon can't be negative. So we're talking about an arbitrary positive number. So for every epsilon greater than 0, for every positive number greater than 0 that you may choose, there is a delta greater than 0. So basically, so far, what they've said is that for any positive number that you choose, there's another positive number such that if 0 is less than the absolute value of x minus a, which is less than delta. And what this is saying, this statement actually says a lot. It may look like a fairly simple statement, but there's a lot here. First of all, when you have x minus a in absolute value like this, what you should interpret this to mean is that you are on the x-axis and there's a number a on that x-axis. That is that number that the limit is approaching up here. All right? And absolute value is used to convey distance. It is among other things, it is a distance measuring tool. So what you're saying here is that for x values there are within all the x values that are within a certain distance of a, first of all, the distance between those x values and a is, if you read it in this direction, is greater than 0. It's basically meaning for all x's that are not equal to a, but are close to a. What you're setting up is something that's sometimes called a delta neighborhood. So you're saying that is if you get within delta in either direction of a, all right, if you get this close to a, then the absolute value of f of x minus L, which is basically saying if you get this close to a, then the distance between f of x and L, well, what is L? Well, L is a number on the y-axis. And what it's saying is that your function, let's arbitrarily say the function looks like something like that. This is your f of x, will be less than epsilon. And what's epsilon? Epsilon is establishing an epsilon neighborhood around L, which basically means that if your limit is L, if the function's limit is L at this a value, then if you set up a neighborhood of x values what that will create is a neighborhood of y values. If your x values stay in here, then your y values will stay in there. And since, again, epsilon can be arbitrarily chosen. That was the very first thing they said. For any epsilon, any positive value, basically what this is implying is any positive value you choose. For any positive value you choose, as long as you get this close to A on the x-axis, you'll get that close to L on the y-axis, right? So let's look at a numerical example with an actual function, shall we? Let's say I was to make the claim that the limit as x approaches 2 of x squared equals 4. Let's say I was to claim that. Now, from what we've previously seen, since x squared is a polynomial, you've been told at this point that you can take 2, plug it in here, and it will tell you the limit value. Again, you've been told that as far as the polynomial is concerned, but you haven't proven it, right? And we're going to. This is one we can do, but I want to mess with it and look it over numerically first. So here's the graph of x squared. Let's say 2's out here. Let's say that 4 is right here, all right? If this limit is as claimed, then here's what has to be true. Someone, if they were trying to challenge you and say, no, I think your limit's wrong, I think you're mistaken. Well, you can prove that you are correct. You can prove that your limit is what you say it is. So their challenge might go something like this. They're going to say, we challenge you with an epsilon value of 1. So what they're saying is, if they're challenging you and they're saying, well, this limit really isn't what you claim, that since your epsilon is 1, they're saying that we challenge you to get function values somewhere between 3 and 5. And again, where the 3 and the 5 come from, epsilon of 1 means within a distance of 1 in either direction. Okay, we challenge you to get the function within 1 unit of 4. All right, then you could come over here and say, well, that can be done. That can be done. All right, I can get this function within 1 unit of 4 if you just let me get close enough to 2. Well, how close? Well, let's see. With a little bit of help from the calculator. If my calculator says that if I'm at 1.75 here and 2.2 over here, then I am within, if I am that close to 2, then I am that close to 4 up here on the axis. Now, how was I coming up with those numbers? How did I get to 1.75 and how did I get to 2.2? I just took square roots. To work my way backwards, I took square roots, and just for an error of caution, I moved a little bit closer on the left and I came a little bit closer on the right. You notice I just took these numbers, the one on the left side I rounded up a little bit to get close, and the one on the right hand side I rounded down just a little bit to get close. Because you notice if you take 1.75 and square it, you get a 3.0625, which means this x value puts me closer than that on the y-axis. And if you take a 2.2 and square it, you get a 4.48. So again, this x value got me closer than I needed to be on the y. All right, and then next, I'm going to take 2 minus 1.75, and that distance is a 0.25. And a 2.2 minus a 2 would give you a distance of 0.2. So, again, my drawing isn't perfect, but I will simply take a smaller number. Because again, with deltas and epsilon, it's just a matter of getting close enough. All right. So they have said, we challenge you to get within 1 unit. That's what the epsilon equal 1 means. Get within 1 unit of 4 on the y-axis. And I answer their challenge with a delta of 0.2. So what I'm saying is that if you get within 0.2 of 2 on the x-axis, you will be within 1 on the y-axis. So they might then turn around and say, oh yeah, well, I still don't believe the limit is what you say it is. Here's your new challenge. Epsilon's 0.5. If you say that the limit is 4, then you should be able to get even closer. You should be able to get somewhere between 4.5 and 3.5 on the y-axis just by getting close enough to 2 on the x-axis. So I could answer their challenge. I can say, all right then, I'm going to take the square root of 3.5, and that's a 1.87. I'll call it 1.9 just for a margin of safety. Take the square root of 4.5 and get a 2.12. Call it 2.1, again, just for a margin of safety. Note that 1.9 squared gets you closer to 4 than 3.5. Note that 2.1 squared gets you closer to 4 than 4.5. Notice that the distance here is a 0.1. Notice that the distance here is a 0.1. This time, purely by chance, I have symmetry. But I've answered their challenge. A delta equal to 0.1, as long as I stay within 0.1 of 2 on the x-axis, I stay within 0.5 of the 4 on the y-axis. And as you can imagine, this challenge could go on and on and on and on and on. And therefore, what we find is that we can prove that the assumption of the limit value being 4 is correct, as long as we allow any. I need to find a delta that for any epsilon that anybody throws at me, my delta will do the job. All right? So what I will have to do is I will have to define my delta in terms of epsilon. I can't just continue taking these epsilons one at a time and doing this because it would never end. So what I'm going to say is I'm going to let my delta equal something in terms of your epsilon, and I need to be able to prove that therefore with that chosen value of delta, this would happen for any epsilon that they throw at me. Not a 1, not a 0.5, any epsilon in existence. So what this brings us to is something called the delta epsilon proof. Okay, delta epsilon proof proves that the limit is what they say it is. All right? And here's basically what a delta epsilon proof is going to look like. Let's say that it is claimed that the limit as x approaches 3 of x fifths, or x over 5, is equal to 3/5. All right, so here's how it begins. We're going to let, now we don't have to start with an if statement. We're going to let the distance between x and 3 be less than some delta value, and at the same time, need a little bit more space here. At the same time, we add that statement in there. So this statement basically says that x and 3 are not the same thing. This statement says that x doesn't equal 3. It says that x is closer to 3 than some delta value. All right? And then we're going to go once this statement's been made, all right, we're going to go see what that does to the function and its limit. Well, the distance between function and its limit is symbolized thusly. Okay, and at this point, it's just a matter of some careful or creative algebra and arithmetic. All right, I noticed, for example, these both have a denominator of 5, so I can factor out a 1/5. Okay, absolute value 1/5 will be 1/5. Okay, what we're hoping to see happen is this expression right here that we use in our original assumption statement. We're hoping it'll show up somewhere here, and now it has. Okay, now since absolute value of x minus 3 is less than delta, that means this is less than 1/5 delta. And what we need is for 1/5 delta to always be defined, or we need our delta to be defined always in terms of epsilon, right? In other words, in the end, I need this this less than statement to end in an epsilon. So if I was to come back up here, what I get to do, sort of after the fact, is I get to now formally define what I want my delta to be. You've chosen your epsilon. Here's what I want my delta to be. I want my delta to be 5 times epsilon. And therefore, yeah, I'm going to run out of some space here. Therefore, this equals 1/5 times 5 epsilon. The 1/5s cancel, and that equals epsilon. So if you read this statement backwards, we've got that epsilon is greater than the distance between the function and the limit value, or if you read it from left to right, the distance between the function and the limit value is less than something that turns out to be epsilon. Therefore, we've proven that the limit is exactly as claimed. All right? Let's try that again. Let's try that again. Let's look at the limit. As x approaches 2 of x squared plus x minus 6 over x minus 2, and they're saying that equals 5. So right off the bat, we're going to let the distance between x and 2, first of all, be positive. We don't want x to equal 2, we just want it to get close to 2. And we're going to let it be less than some delta value. All right? Let's see what that does to the distance between the function and the limit. Well, the distance between the function and the limit is written that way. So the first thing I'm going to do, again, algebra, arithmetic, and such as that has to happen, is I'm going to get a common denominator. Common denominator is going to be x minus 2. And that's how I get it written with the common denominator. That's going to be an x squared plus an x minus a 6 minus a 5x plus a 10 when you distribute a minus and a 5 through here. I'm going to clean that up. Plus x and a minus 5x is a minus 4x. A minus 6 and a plus 10 is a plus 4. Okay. Next, I'm going to factor on top. As I've said before, don't forget that you know from algebra. So this is going to be an x minus 2 times an x minus 2 over an x minus 2. One of the x minus 2's cancel. And that equals the absolute value of x minus 2. And again, this is the expression I'm always hoping will show up, that being the same one as I had up here. I've already said that this is less than delta. So to make this less than epsilon, I can simply make delta and epsilon the same. So someone comes along and says, I want you to get within epsilon of this limit value. My delta can be the same as their epsilon, and my function value will be within that distance from the epsilon that they've chosen. All right, so let's try once more. Let's try at least one more limit. There's one here that's I've always found to be a little bit interesting. One of the things we claimed is that the limit as x approaches a of c is equal to c. Let's see if we can prove that that's actually correct. I'm going to let x and a get within delta of each other, but not equal each other. And let's see what happens up here. Then the function value and its limit, the distance between them will be what? It will be 0. And 0 is always less than epsilon, because we've specifically said epsilon is a positive number. Therefore, delta can be any real number. This function is always within a distance of c from c because they're the same thing. So in this particular instance, our delta can be anything. You get any distance away and you are at your limit value with that constant function. All right, so this is just an idea of how some of the delta epsilon proofs are going to work. Give them a try for yourself, and let me know if there's any problems.